Computational Efficiency in Expansion. Now, before we dive into the new material, let's quickly recap what we've already covered. In our previous lessons, we established a very important property, that the determinant of a 3x3 matrix can be expanded along any row or any column, and no matter which path you take, you will always arrive at the exact same mathematical result. However, even though the final answer remains the same, I want you to notice that the amount of effort and the time you spend on your calculations can vary significantly depending on the specific row or column you choose. Some paths are much more taxing than others. That brings us to the core purpose of this subsection. We are going to focus on a work smarter, not harder approach. I'm going to provide you with specific strategies designed to help you minimize the number of calculations you need to perform. By doing this, you won't just save time, but you'll also significantly reduce the likelihood of making those frustrating arithmetic errors that often happen during long expansions. So, let's look at how we can make our calculations much more efficient. Welcome, everyone. Let's begin today's session by looking at our first slide, titled Computational Efficiency in Expansion. The core strategy, the power of zero. Now that we've established that you can expand a determinant along any row or column and get the same result, let's talk about how to do this without unnecessary struggle. The core strategy we are going to use is based on a very simple, fundamental principle, the zero property of multiplication. You already know from basic arithmetic that anything multiplied by zero is zero, right? Well, that is the secret weapon here. Think about how we perform a determinant expansion. We take an element from the matrix and multiply it by its corresponding minor. Now, if that element happens to be zero, the entire product for that term becomes zero, no matter how large or complex the minor might be. Mathematically speaking, if you choose to expand along a row or a column that contains zeros, you are essentially giving yourself permission to skip the heavy lifting. You don't even need to calculate the minors for those specific elements, because you already know they won't contribute anything to the final sum. This leads us to what I call the golden rule of determinants. Always scan your matrix first and choose the row or column that contains the maximum number of zeros. By doing this, you'll see in the next slide exactly how this step-by-step process works in practice. Step-by-step guide to efficient expansion. First, step 1, scan the matrix. Before you pick up your pen to calculate anything, I want you to take a moment to simply look at the entire matrix. Don't just jump into the first row. Instead, look across all 3 rows and all 3 columns. Step 2, count the zeros. This is where you apply the strategy we just discussed. Your goal is to identify which specific row or column has the highest frequency of zeros. This is your target area for expansion. Step 3, evaluate ties. Now, what happens if you find a tie? For instance, if row 1 and column 2 both have 1 0, don't panic. In this case, look for the path of least resistance. Choose the row or column that contains smaller integers, such as 1 or -1. This keeps your remaining multiplications as simple as possible. Step 4, apply the sign convention. This is a crucial step where many students lose marks. Once you have selected your optimal row or column, you must remember to apply the sign factor, which is -1 raised to the power of I plus j, associated with those specific positions. Always double-check your signs before proceeding. And finally, step 5, calculate the non-zero terms. This is the reward for your efficiency. Since we know that any term multiplied by 0 will vanish, you only need to focus your energy on computing the minors for the elements that are not 0. Now that we understand the golden rule of using zeros to our advantage, let's break this down into a practical, step-by-step workflow you can use every single time you see a matrix. In the next slide, I'm going to show you a side-by-side comparison where we put this exact 5-step process into action to see just how much time and effort we can save. Comparative example, the hard way versus the efficient way. Now that we've discussed the theory behind using zeros to our advantage, let's put this into practice with a concrete example. Take a look at this matrix. It is a 3 by 3 matrix, where the first row consists of 2, 3, and 1. The second row contains 0, 5, and 0. And the third row consists of 4, -1, and 6. To demonstrate the difference in effort, let's first try method 1, which I'll call the hard way. Suppose we decide to expand along the first row. As we learned in the previous slides, this means we have to calculate 3 separate 2 by 2 determinants. Starting with the first term, we take the element 2 and multiply it by the determinant of the minor containing 5, 0, -1, and 6. This gives us 2 times the quantity of 5 times 6 minus 0 times -1, which simplifies to 2 times 30, resulting in 60. Next, we move to the second term. We take -3 and multiply it by the determinant of the minor containing 0, 0, 4, and 6. This calculation is -3 times the quantity of 0 times 6 minus 0 times 4, which is simply -3 times 0, giving us 0. Finally, for the third term, we take 1 and multiply it by the determinant of the minor containing 0, 5, 4, and -1. This is 1 times the quantity of 0 times -1 minus 5 times 4, which is 1 times -20, resulting in -20. When we sum these up, 60 minus 0 minus 20, we get a final determinant value of 40. It works, but notice how much arithmetic we had to perform. Now let's look at method 2, the efficient way. If we apply the golden rule from our second slide and scan the matrix, we'll notice that the second row contains 2 zeros. This is our expressway. When we expand along the second row, our calculation looks like this. -0 times the determinant of the minor containing 3, 1, -1, and 6, plus 5 times the determinant of the minor containing 2, 1, 4, and 6, minus 0 times the determinant of the minor containing 2, 3, 4, and -1. Because of the zero property of multiplication we discussed earlier, the first term and the third term both immediately become 0. This leaves us with only one single calculation to perform, the middle term. We just calculate 5 times the quantity of 2 times 6 minus 1 times 4, which is 5 times the quantity of 12 minus 4, leading to 5 times 8, which equals 40. As you can see, both methods yield the exact same result of 40. However, the observation here is key. Method 2 required significantly fewer multiplications and subtractions. By choosing the path with the most zeros, we've drastically reduced the workload and, more importantly, minimized the chance of making a manual arithmetic error. This brings us to our next slide, where we'll use an analogy to help you remember why this strategy is so vital. Real-world analogy, resource optimization. Think of calculating a determinant as navigating a map to a specific destination. In this scenario, the final value of the determinant is your destination, the place you must arrive at. As we saw in our previous examples, there are multiple different roads you can take. These are the various rows and columns of the matrix, and all of them will eventually lead you to that same destination. However, not all roads are created equal. Some roads are plagued by traffic jams, which represent complex numbers, large integers, and heavy, tedious calculations that slow you down. On the other hand, some roads are like expressways. These are the rows or columns containing zeros, allowing you to glide through the calculation with almost no resistance. So, when you are faced with a matrix, choosing the row or the column with the most zeros is exactly like choosing the expressway. It allows you to reach your destination much faster, with significantly less effort, and most importantly, with much less stress and a lower risk of making a mistake. Now, I want to take a moment to step away from the numbers and look at the bigger picture using a real-world analogy. This should help you internalize why we use these strategies. As we move into our next slide, we will look at some specific pitfalls to watch out for so that even when you are on the expressway, you don't accidentally take a wrong turn. Common mistakes to avoid. Now, before we wrap up our session and move on to our final summary, I want to pause and discuss some common pitfalls. Even when you are using the efficient strategies we discussed earlier, it is very easy to fall into certain traps that can lead to the wrong answer. First, let's talk about ignoring the sign convention. This is perhaps the most frequent mistake I see. You might find a row or column with many zeros and feel great about your choice, but you must remember that the position of your non-zero element dictates its sign. For instance, in a 3x3 matrix, if you are looking at the element in the second row, first column, or the second row, third column, those positions always carry a negative sign in your expansion. Don't let the zeros distract you from the underlying sign pattern. Second, watch out for the habit of overcalculating. I've noticed that many students develop a muscle memory of simply expanding along the first row, no matter what the matrix looks like. While this works, it's often the hard way we saw in our previous example. I want you to train yourself to always pause and scan the entire matrix before you pick up your pen. Take that extra second to look for those expressways we talked about. Finally, even when you are using the efficient method, be extremely careful with sign errors within the minors themselves. When you are calculating a 2x2 determinant, specifically, the product of the top left and bottom right elements minus the product of the bottom left and top right elements, it is very easy to lose track of a negative sign, especially when the matrix contains negative integers. Keep these 3 points in mind, and you'll significantly increase your accuracy. Now, let's look at our final slide to consolidate everything we've learned today. Key takeaways. First, always keep your ultimate efficiency goal in mind. Your objective is to minimize the total number of multiplications and additions you have to perform. The less arithmetic you do, the less chance you have of making a silly mistake. To achieve this, your primary strategy should always be to expand along the row or the column that contains the most zeros. As we saw in our earlier examples, zeros are your very best friends because they allow you to skip entire calculations. Now, what if you encounter a tie? If you have two different rows or columns that have the same number of zeros, use your secondary strategy. Choose the path that contains the smallest absolute values, such as 1 or -1. This keeps the remaining numbers small and manageable. It is also vital to remember the principle of consistency. No matter which row or column you decide to pick, the final scalar value of the determinant will remain exactly the same. The math is robust, so you can trust your choice as long as your calculation is accurate. Finally, I must leave you with one critical reminder. Never forget to verify the sign factor, which is -1 raised to the power of the sum of the row index and the column index. Even when using the most efficient path, a forgotten negative sign can lead you to the wrong answer. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways to ensure you have a solid grasp of how to approach determinants with maximum efficiency. Keep these strategies in your toolkit, and you'll find that calculating determinants becomes much more streamlined and much less error-prone. Great job today!